Welcome. This is complex analysis continued, and this is going to be the sixth session on path integrals. Today we are going to specialize to a kind of path integrals which I call Cauchy type integrals. This is going to play a very crucial role in the development of Cauchy theory, which is the next series of lectures on. Right? Okay, so let us get started. So as usual, let U in C be open, non-empty, and gamma a path from AB to U, right? And this denotes the track of gamma, which is equal to gamma of AB, which is a subset of U. So let F be a continuous function from gamma to C. Okay, and fix a point Z not in gamma. So I have, let us give a picture. In fact, I don't have to worry about this. Let gamma be any path in C. Okay, so I have this. This is my gamma track. Okay, and take any Z which is not there. Maybe make it Z not or A. Maybe call it A. A not in gamma. Alright. Okay. Now I want to define G of Z to be by this integral f of w by w minus z for every z in U. Okay. So therefore G is a function from where. First notice that this over gamma. This makes sense. Why? Because this w is of the form gamma t, and gamma t minus z 1 upon that makes sense because z is not in the track of gamma. Okay, right. Therefore this is a continuous function, right? A t going to f of gamma t by gamma t minus z is continuous, right? Therefore I can talk of path integral. So this is called Cauchy type integral. So what is very important about that? F is a continuous function on the track of gamma and z is not on the path. Okay, then I am talking about path integral of fw by over w minus z. Remember, we had already seen such a thing. Do you remember that? We had seen integral of this of form where gamma is gamma t equal to a plus r e power a t. Okay, yeah, a special type of Cauchy integral we had already seen. This is also a Cauchy type integral, and we computed this to be 2 pi I. Do all of you remember that? Okay, so this is a Cauchy type integral. So the theorem we want to prove is the following. This theorem tells us how to generate analytic functions. Okay, we already talked about analytic functions when we talked about differentiation chapter. Now we are in the path integral. Okay, we already gave examples, but this is going to be the most important example. So let gamma from AB to C be a path, and let F from the track of gamma to C be continuous. Okay, and for Z in C minus the track of gamma, define G of Z to be integral over gamma of f of w by w minus z dw. This is the path integral. If just for sake, let me rewrite this. This is a to b f of gamma t by gamma t minus z and gamma prime t dt. Assuming it's a C1 path, otherwise break into subintervals, okay, summation of subintervals, etc. Okay, hereafter whenever we need, we'll simply assume C1, and if it is piecewise C1, you know what to do. Okay, integral will be over summation gamma restricted to ti minus 1, that is integral summation I equal to 1 to n and ti minus 1 to ti and this summation. Okay, those things I don't want to repeat, so please understand. So without loss of generality, we will assume gamma is C1 on its domain and work with that. So what is the conclusion? Then G from C minus gamma. Notice that this is analytic. Okay. First notice that this is open. Why? Because gamma is a continuous function on the closed and bounded interval, right? Therefore, which is compact set. Therefore, the image of gamma, namely the track of gamma, will be compact, and hence it's closed, right? So it's a closed subset of C, and its complement is what we are talking about. That is the domain of G, that is open. Okay, so the domain of G is an open set, so we can talk about analyticity. This is the idea. Okay, now how do I prove that? The proof is extremely simple. Okay, so let me again draw the picture. Suppose this is gamma. Okay, fix. So to prove, so let us understand. To fix an A in C minus gamma. Okay, so what do I have to do? I have to find, to prove it analytic, I have to find an R positive, so that BR is contained in C minus the gamma. Okay, find an R positive, so that, and constant Cn in C, so that what should I do? F of z, or sorry, G of z equal to summation Cn z minus a to the power n. N is running from 0 to infinity. For this should be true for every z in B. Okay, this is what I want to show. This is what you want to show, right? So because it's analytic, meaning given any a in the domain, okay, it must be a power series in powers of z minus a in a disk around a. Is that clear? Pause, review. This is what you have to show. Right? Okay. So how do I do that? Right? Okay. Let us look at it. So notice that t going into distance between gamma t minus a. This is always positive because gamma t is not equal to a for any t and ab. Okay, so this a and that a may get confused. Okay, that's a slightly unfortunate notation, so maybe I should use z naught. You see that this I keep changing. Okay, z minus z naught to the power n z naught, and z naught equal to z naught. Okay, you understand this? Yeah, when it chose a, I forgot. Okay, the domain of gamma is an interval AB. Okay, that's why you're right. This is positive, right? And remember, this is on the interval AB. This is a real valued continuous function on this interval, which is closed and bounded. Therefore, it attains a minimum. Say at t naught in AB. So, what does it mean? Distance between gamma t and z naught is greater than or equal to distance between gamma t and gamma t naught and z naught. Call this as something like 2r. Right? This is a, because this is always positive, that positive number I call it 2r. You follow that? Okay. So what I am going to do is this one. So I have a z naught here. Okay. I choose an 2r. Okay. This is 2r. The minimum distance may be 2r. I am choosing this as R. Okay, so we are going to choose on this R. Okay, so R equal to the, what is this, minimum of distance between gamma t and z naught, okay, by 2 as t varies over ev. Right, so we found that R. All right, so the next trick, this is the standard trick. Do you remember? Okay, this is the one which we are going to use in every Cauchy type integral. So what do I have in the denominator for g of z? So g of z is, remember, integral over gamma of f of w by w minus z. Where is w? W is in the track of gamma. Okay, okay, where I am going to allow my z? I am going to take z only in b z naught of r. Okay, right? Okay, so my z is going to be somewhere here. Where is the cursor? Maybe I should check. Let me, sorry, excuse me, I'll just make a pen options, very thick eraser, highlight. There is something where I can do options. Pencil cursor, yeah, yeah, this will make my life easy. Okay, my z naught is going to be, my z is going to be some point here in the open disk b z naught of r. Okay, so the trick is, well, 1 by wz, okay, we expand it in geometric series in powers of what? Z minus z naught, because that is what we want to show, right? We want to show powers of z minus z naught. Okay, so but I have 1 by 1 upon w minus z. Do you remember when I proved, again go back, when I proved f of z equal to 1 by z is analytic? Okay, then if you gave me an a in c star, okay, on c star, then what did I do? 1 by z I wrote as z minus a plus a. Therefore 1 by z will be that. You remember that trick? The same trick is what I are going to do. Please recall. Okay, so this I am going to do as w minus z. I am going to write as w minus z naught plus z naught minus z. This is w minus z naught plus minus z minus z naught. Right? Okay. Now let us look at what do I know about w minus z naught modulus. W is gamma t, right? And therefore this is always greater than or equal to 2r. Do you remember that? But what do I know about z minus z naught in modulus? That is less than r. Is that point clear to all? Yeah. Therefore 1 upon w minus z I can write as 1 upon w minus z naught minus z minus z naught. So what do you think I should do now? The same thing. You see, this is why learning something not just for understanding, okay, just checking rigorously line by line is not enough. If you have understood that proof, you know what I did there. What I did there was the same thing. 1 upon z, I took at 1 upon a into 1 plus z minus a by a. So if mod z minus a by a is less than 1, I can use geometric power series. Geometric series for this. Okay, same trick is what we are going to do. So that's why you should learn always well. Whenever you learn something, if something similar has done, I should revise that. Okay, so that later it is completely in my mind. At any time I can bring it back. Okay, you don't have to make great effort. The same way as you know multiplication table now. Anyway, so I can take this out, w minus z naught out. Okay, then it is going to be 1 by z minus z naught by w minus z naught. Do all of you agree with that? Yeah. Now what do I know about z minus z naught by w minus z naught. Okay, this is less than or equal to r, and 1 upon that is less than or equal to 1 by 2 r, therefore this is less than half, right? Therefore I can expand this 1 by w minus z naught into, this is what is going to be there, z minus z naught by w minus z naught power n equal to 0 to infinity. Okay, so is that clear to all? Alright, now notice that your z is fixed and z naught is also fixed, and z is fixed. If you want it, allow it varies in b z naught of r. That's not important for me. Okay, right? This is uniformly convergent by Weierstrass-Helmstedt. Yeah, because mod w minus z naught is fixed. That is okay for any w. It is bounded by 1 by 2r, and this is this is bounded by geometric series half power n. Do all of you understand that? Yeah. So this is in modulus 1 by w minus z naught, that is less than or equal to 1 by 2r, and this fellow is bounded by 1 by 2 power n 0 to infinity. Therefore I can apply 1 by 2r will come here. Therefore I can apply Weierstrass test. Okay, and this is true for every w on the track of gamma. Alright, therefore this series is uniformly convergent on the track of gamma. Please understand. Pause. I'm sorry, I should have given pause review proceed long time ago. Yeah, so let us look at, therefore what I have shown, I have shown by 1 by, okay, or this series z minus z naught power n by w minus z naught power n plus 1 when n equal to 0 to infinity, okay, is uniformly convergent on gamma. But what is this object? Okay, right. Now let's look at f. See, f of w, this is bounded because f is a continuous function on the trace of gamma to c, and this is a continuous function on a compact set. If you want, just look at t going to f of gamma t. This is a continuous function on a closed and bounded interval modulus if you want. Right? Continuous real valued function, therefore it's bounded. Therefore, model this is less than or equal to m for all t. Right? Okay. Therefore, this object, namely f of w into z minus z naught power n by w minus z naught power n plus 1 n equal to 0 to infinity is uniformly convergent on mod gamma, again by Weierstrass test. Okay, this fellow is less than or equal to m, this fellow is mod w minus z naught will be there, that's less than or equal to 1 by 2r, the other one is 1 by 2 power n. Okay, this is a Weierstrass test. Yeah, have you understood? So this is PRP. Alright, therefore now let's look at integral over gamma of f of w minus w minus z, where z is in the z naught of r. Okay, this is nothing other than integral over gamma of this object. Okay, there is an f of w if you want, because that does not involve here, 0 to infinity of z minus z naught power n by w minus z naught power n plus 1. Okay, into dw if you want. This is uniformly convergent, right? Therefore I can interchange the sum and the integral. Therefore this is going to be n equal to 0 to infinity of integral f of w by w minus z naught power n plus 1 dw. Notice that z minus z naught power n does not involve the parameter for the integrand, namely w. Therefore, this I can take it out as z minus z naught power n. Have you understood this? Yeah. So this is true for every z in B z naught of r. Okay, this is your g of z. So if you call this as Cn, so what do I have? I have n equal to 0 to infinity of Cn z minus z naught power n. Right? And z naught in C minus this is arbitrary. Therefore, G is analytic on C, the complement of the trace of gamma. Okay, pause, review, proceed. So we had proved the result. Okay, that it is analytic because around Z0 there is a disk on which F is G is represented as a power series in Z minus Z0 power n. Therefore, it is analytic by our definition. Yeah. So this is the beauty. Okay. Now let's just take one step. Now since it's a power series, we know G is also infinitely differentiable. And if it is a power series, these Cn's have a meaning. What is it? Okay. This is the nth derivative of G at Z0 by n factorial. Right? Therefore, I know what is the nth derivative of Z0 of G. This is going to be integral over gamma of 1 by n factorial into f of w by w minus Z0 to the power n plus 1 dw. Go back. What is my Cn? That Cn has to be this. That's what I'm writing. You follow that? So we even know the derivative. The nth derivative of the analytic function G explicitly in terms of some type of integral. And this is not Cauchy integral because the powers in the denominator w minus z0 comes with higher powers. Only when w minus z0 comes with power 1, then we call it Cauchy type integral. Do you follow that? So this is actually a version of Cauchy integral formula. Notice that some of you who had seen complex analysis earlier, I have not assumed this gamma is circle, closed path, nothing of that kind. Yeah? Right. Okay. In particular, what is G of Z0? That is your C0. That is nothing other than f of w by w minus Z0 because n has to be 0. Alright. So this is again Cauchy type integral. This is Cauchy type integral formula for derivatives. So let's come back and understand what do you think we have done in path integral. Okay, there is something I want to say, but before that, more or less whatever I wanted to say about path integral is over here. So we define path integral, okay, and we establish the usual properties, like, and also we establish the ML inequality. Using ML inequality, we also said if fn's are continuous on the trace of gamma, if fn converges to f, then f is continuous on gamma, the trace of gamma, and integral fn over gamma, path integral of fn over gamma converges to path integral f over gamma, and similarly so we wanted to make use of that, right? So we put two results in path integral. One is if I have a connected open set U and if f is a continuous function from U to C, then it admits a primitive if and only if integral of f over any closed path gamma is 0. This is what we did in the last session. Yeah. And today what we did was any Cauchy type integral. What is meant by Cauchy type integral? It is of the form integral of over gamma, a path integral of the type integral of fw by w minus z. Okay, where z is not on the path, trace of the path. Okay, these are called Cauchy type integral. We said any Cauchy type integral is analytic on the complement of the trace. Right? Keep these 2 points in mind. Okay, this is the outcome of path integral. So the next series of lectures, the so-called Cauchy theory, what we want to prove is any holomorphic function admits a local primitive, and two, any holomorphic function is analytic. If I want to prove, what do you think I should do? From the first result, I have to prove, if I want to say it admits a local primitive, maybe I have to assume, let us take an open disk, okay, around a point where f is holomorphic, then let gamma be any closed path in the open disk, then integral of f over that closed path must be 0. This is what we just said, right? If f is a continuous function, a connected open set, it admits a primitive if and only if integral of f over any closed path gamma is 0. So if I want to say any holomorphic function has a local primitive, what should I do? I have to prove the result. What is the result? Take a point holomorphic function, take a point in its domain, take an open disk, and take any closed path in the open disk, then integral of f over that closed path must be 0. This is Cauchy's theorem. Second thing, I want to prove it's actually infinitely differentiable, but actually I prove something stronger. It is analytic. To say it's analytic, what should I do? I have to show if f is a holomorphic function, I can find a Cauchy type formula. That is, my f is defined by a Cauchy type. That is, my f of z is equal to integral of fw by w minus z, where it is over a path gamma. Okay, we are going to say it's a closed path, it's a circle or whatever it is. Let's not worry about. So I have to show my f holomorphic function can be represented as a Cauchy type integral. Remember, here I define g equal in terms of f, there it is f itself in terms of f. In f of z is going to be integral over gamma of f of w by w minus z. Some kind of. If I do that, I have done. Do you understand? These two results are we are going to derive in the next series of lectures. Okay, that's going to be the next chapter or whatever you want to call it, next part of the course. Does it make analysis easy now, complex analysis? Please go back. Please review whatever I said, replay, and go back to the relevant things which I proved. Okay. Then the last session I proved f admits a local primitive in a connected open set if only if integral f over any closed path is 0. Okay, that's what is very easy on today. Okay, right. Now let's go back to a few more typical applications of Cauchy type integral. So remember, I proved if gamma is a circle, let us say gamma t equal to a plus r e power I t 0 less than equal to 3 less than equal to 2 pi, then integral of 1 by w minus a, okay, over gamma, this is 2 pi I, or 1 by 2 pi I is 1. And if I define gamma n t to be, or maybe I did as k, a plus r e power I k t, t again in 0 to pi, then in that case we saw that 1 by w minus a over gamma is 1 by 2 pi I is k. And we also gave a geometric interpretation. What is that? The circular path gamma, let us look at a picture. This is circular path, this is my a, and this is my gamma. Okay, gamma goes around a once. If I look at gamma k, if k is positive, okay, then gamma k goes around a in the anti-clockwise direction k times. If k is negative, it goes around a k times anti-clockwise direction, right? Now if this is a geometry, then there is a very natural question I can ask. Suppose I take some z here, which is in the BAR, right? That is, it is inside this area enclosed by the circle. In this case, it's an open disk BAR, right? Then what do you think about my gamma k? Gamma k also goes around z k times, right? If k is positive, in the anti-clockwise direction k times. If k is negative, in the clockwise direction k times, right? So can I prove that? What is that I want? Please understand. Huh? Please pause, review if necessary, rewind, go back and see what I want to ask. So that means I would like to ask if my z is in VAR, then if I form the integral w minus z, whereas my gamma is again the same, gamma t equal to a plus r e power a t, 0 less than equal to t less than equal to 2 pi, and 1 by 2 pi I if you want, is it equal to 1? That is, if z is in the area enclosed by the circle, namely in the open disk BAR, then also I want to say gamma goes around z one time. It's okay, it winds around. Okay, one usually says goes around or winds around. I had already used such words. Okay, so what do you think I should know? Remember, what I know earlier is recall. We know this. If I take this gamma as above, and if I look at dw by w minus a to the power n, we know this is equal to 0 if n is not equal to minus 1 equal to 2 pi I when n equal to minus 1. Do you remember this? This is true for every natural integers z. We have proved this. We had already proved that. Yeah? Yeah. Keep this in mind. We are going to use that. Yeah. We had also seen this thing. Yeah. Keep it. But if there is something different, I will come. So how do I compute this? What all I know is, I know 1 by w minus a 1 by 2 pi I, the path over gamma, the interval over gamma is 1. This I know. Okay. But what you have is w minus z. What do you think now you do? This is again a Cauchy type integral. Alright. So just now you saw how I did 1 by z analytic function, how I proved g of z equal to f of w by w minus z integral over gamma. That also how it's analytic. Okay. All these things, what is the trick? So you know the trick, so we can do that. So what do I do? Look at w minus z. I can write it as w minus a plus z minus a. Minus z minus a. Yeah, let me write it clearly. Yeah, now remember z lies in VAR, therefore modulus z minus a may be some rho, which is rho is strictly less than r, right? Therefore again I can do the same trick, w minus a, take it out, 1 minus z minus a by w minus a. Therefore mod z minus a by w minus a is rho by r, which is less than 1. It's a fixed constant. This is for every w in gamma. Yes. So proceeding as earlier, therefore I can 1 by w minus z, I can write it as, since this is modulus, this is less than 1, I can apply the geometric series. Therefore what do you think I am going to get? Yeah. So I am going to get 1 by, remember this is 1 over, right? This is w minus z, therefore I have to put 1 over, therefore it will be this. Therefore it's going to be z minus a to the power n by w minus a to the power n plus 1 n equal to 0 to infinity. This is uniformly convergent. On what? On gamma. Right? Therefore, by our earlier result, I can gamma, this is same as this object, Okay, but I can interchange the sum because this is uniformly convergent over gamma, right? Well, therefore this is this. Now remember z minus a to the power n, the integral is only over w, therefore this is a cons. This is, as far as integration is concerned, this is unnecessary. N equal to 0 to infinity of, okay, 1 by w minus n plus 1 dw over gamma. Yeah. Now let's recall what I said. I said this, if you want put n plus 1, then what you want is n plus 1. Okay, n equal to 0, right? Okay. So this object is 2 pi I when if n plus 1 is 1, that is n is 0. Are you following what I am saying? This must be 1, therefore n must be 0. Otherwise 0 if n is not equal to 0. Right? Therefore this object turns out to be n equal to 0 to n z minus a to the power n into either 2 pi I when n equal to 0, otherwise it is, therefore this is equal to 2 pi I. This is n equal to 0. When n equal to 0, this is 1, therefore I get a 2 pi I. At all other points, this is a something times 0, therefore it is 0. Do you follow that? Please pause, review, proceed. So let's recall what I have shown is, if gamma t is a plus r e power I t, t in 0 to pi, 2 pi, and my z is in bar, okay, my gamma winds around z one time, once. What is the meaning? Look at 1 by 2 pi I integral over gamma of dw by w minus z is 2 pi I. This is what you proved. This is all word, okay, just jargon. Okay, this integral equal to 2 pi I, that's all we have proved. Now what is the question you would like to ask? Suppose I take gamma k of t equal to a plus r e power I k t. Do you think 1 by 2 pi I integral of dw by w minus z over gamma k is k, where z is of course in bar? The answer is easy. Go back. See, what did I do? The only thing which this is going to be surviving is when n is 0. When n is 0, we know dw by w minus a, n is 0, therefore dw by w minus a over gamma k, that we know is 2 pi I k, right? Therefore this is true. Make sure you understand this, okay? Okay. Therefore, what is the intuition now? Go back. Therefore, if I take gamma k also, okay, if my z happens to be in the open disk, that is in the area enclosed by gamma k, right? My gamma k goes around z also k times. Okay, if k is positive in the anti-clockwise direction k time, if k is negative, that means it goes around z in the clockwise direction. Have you understood this? Okay. So last one, I will stop with that. What is the last question? Suppose I have the same thing, a path A, and suppose my z is outside, that is mod z minus a is strictly greater than r. See, z on the circle gamma I cannot accept, right? So gamma t is as usual a plus r e power I t. If z is there, so this is my gamma. How many times it goes around z? Intuitively it should be 0. Do you accept it? Yeah, intuitively gamma winds or goes around Z 0 times. Even if I take gamma k, it should be 0 times. Yeah, because it is outside, right? So what do I want to know is, therefore I form the same thing, gamma dw by w minus z is it equal to 0. The Cauchy type integral corresponding to that, where z is not in the closed. So I'll just indicate the proof. I'm not going to spend much time because many times you have learned how to do that. The same trick. 1 by w minus z is 1 by w minus a minus z minus a. Now remember, this is my, okay, maybe this is a, this is w is here, okay, this is r, but this is strictly greater than r, right? Suppose I call this r equal to distance between z minus a, that is strictly greater than r, right? Therefore if I want to expand again as a geometric series, what should I pull out? W minus a or z minus a? So what should I pull out? So I have 1 by w minus z, therefore w minus z, I want to write as w minus a minus z, sorry, z minus a, yeah. So I pull out z minus a out with a minus sign, therefore it's 1 by w minus a by z minus a, yeah. Therefore 1 by w minus z is going to be minus 1 by z minus a into power series, which is w minus a power n by z minus a power n equal to 0 to infinity. Therefore it's going to be n equal to 0 to infinity of w minus a to the power n by z minus a to the power n plus 1. And this is uniformly convergent on gamma, therefore I can interchange the integral, okay, dw by w minus z over gamma is going to be, take the integral out over gamma of this object, w minus a to the power n by z minus a to the power n plus 1, the whole thing into dw. But z minus a to the power n plus 1, that is independent of the integrator variable, therefore it's going to be, yeah, integral of 1 by z minus a to the power n plus 1 and w minus a to the power n dw over gamma. But we know this is 0 for every natural number greater than or equal to 0, right? So we proved the result. Therefore what do you think we have proved? The same thing works for gamma k, because here I will have a gamma k, but we know this is again 0. Therefore our intuition is correct. So this is my a and this is my z, then gamma, namely gamma is this, winds around z, z not in bar 0 times. That is, it does not wind around at all. That geometric intuition is proved. Okay, therefore this kind of Cauchy type integral, we are going to call it as winding number, that is 1 upon 2 pi I integral dw by w minus z. We will call it a winding number of gamma around z, provided gamma is closed. Okay, this I'm just going ahead, I'm just saying, keep that jargon in mind, but all these Cauchy type integral will play an important role. So learn these things, go through it twice, and please remember, we proved two important results about existence of primitives and a Cauchy type, a function defined by a Cauchy type integral is analytic outside the track of the path. Learn these things well. We'll meet again. Take care. Stay safe.